must be that page that's on the top. Great. If you look at the 5th percentile Douglas fir compression perpendicular to grain, you see 3.6 megapascal. And you see the same number for number 1, number 2, or select structure. It doesn't matter what the knots are like. This is just squashing the straws. It's a very consistent number. If you go over to, and that's 5th percentile, if you go over to the other side, Douglas fir, compression perpendicular to grain, you get 6. That's the average for clear specimens. Remember when we were looking at bending, for the 5th percentile we got 10, and for the average we got 90, or 88.6. There was a factor of nearly 9 to 1 between the 5th percentile and the average of small clear. Now the difference is 3.6 to 6.0. In other words, it's about 50%, 1.5, not 9. So it's much more predictable. So something like somewhere between 3.6 and 9 is where we expect this to go. Let's see. So what's the area we've got now?
The area is 340 by 81,900 millimeters squared.
What's 340?
Yeah.
Yeah. And so, what's that prediction of the failure load if we take
3.6?
If we take 3.6?
That gives us about 295 kilonewtons.
295 kilonewtons. Now, realize that's a lot larger than the load it took to break the beam and bending, but we're now just doing straight compression, not bending. And so it takes much more load to produce that stress that way.
Oh, I'm sorry, my bad.
Yeah.
210.
Doesn't matter. 210. The bending was, we got to 190.
We went to about 200.
About 200. So it's about the same. But we're going to a much lower stress. We got to 32 megapascal or something in the bending test. Here we're not going to get much above 4. Have a look at some of these tracks, which as they load will close up. And if you watch very carefully, you'll be able to see when it gets shorter. You won't see it yet, but if you wait a while, you will. It'll get shorter and it'll get wider. And now I'm starting to squash some of the straws. So it makes a lot of noise this way, but it's much less dangerous. These are just squashing straws. I think the failure load is about 210 for the 5th percentile.
Are we going to get a quiz today?
And about 50% more for the 5th.
I hope not.
I don't have time for him.
So we're about halfway to failure if it's 5th percentile. By the way, look at this. We do have a deflection here. No? Oh, just the head. The head. Yeah. So we have a relatively, it's not a straight line, but it's showing some deflection. And the head displacement, that's not right. Is it 23 newtons? Oh, okay. Yeah, no problem. 295 is the prediction. Yeah, 295 is the predicted failure load for the fifth percentile number. Okay, start.
I mean, where did you say 50%?
This is 5 millimeters.
Where did you say 50%? I don't know.
Yeah, so we're about 2.5 millimeters
it.
now. And we can calculate the Young's modulus this way, and we'll find it's much, much lower than the Young's modulus parallel to the grain. The wood is not as stiff and not as strong.
So at this load, at 160 kilonewtons, the stress is about 2.75 megapascals.
And if you take 3 millimeters and divide by 240,
What's this 173 actually? Kilometers, right?
12 per thousand.
yeah, and so if we calculate E, if we divide,
And then he's calculating
divide the
megapascals.
stress by that stress was 2.5. What did you say?
What was the stress? Do you record it? Did you record it?
Anyone record it?
2.75. megapascals.
Yeah. So the stiffness perpendicular to the grain is about 220 megapascals. Steel is 200,000 megapascal. This is 200. The wood parallel to the grain should be about 9,000. Perpendicular to the grain is 200. So it's very soft in this direction. We're going through. Yeah. It's funny, we always have failure with that load, Sean.
Anybody want to put their hand there?
Expanding?
I can't see it yet. It looks like 240 still.
It's like somebody puts their hand under before it starts compressing. Probably. How do you know that? It's just like percent. Is this all of them?
Yeah.
Percent.
And the other side of the table, these are the coverage.
So we are starting to see some curving over. Just to make a layer out of me, it's definitely up again.
You're gonna watch this when you get home.
Yeah, I'm probably gonna upload it onto the EngSci group.
But they're all gonna see this.
Yeah,
Are they gonna
if you
hear
want
it?
memories.
Are you gonna hear me talk then?
Yeah, I guess.
Oh, okay. Hi. Hi guys.
Now we're
like an
starting to hear
episode
it
called
creaking and
I
groaning.
know. Yes. The cracks for
I think you can see the cracks in this. I can see colors on.
2.8 megapascals now.
remember we had a nice wide crack here? You can't see it anymore, can you? It's all closed up, so it's squashed closed. Yes?
The other way you can like fix a piece of wood.
It comes from the lumberyard. Lumberyard. Timber merchant. It could well be from British Columbia. It's Douglas fir. It's mainly grown in British Columbia. It costs quite a lot. We've spent several $1,000s on this.
One block?
No, not one block, but the whole lot was
Yeah. So about 2,000-3,000?
6,000.
Well, for a year, yeah.
Yeah. So this week we're spending about $6,000 on the timber. that
Way to
we're
go
breaking.
inside. They spend nothing.
PFC sticker.
If you want to use this
How do they
machine
put it on
commercially,
everything?
it's something like $600 an hour.
Like usually
So
it's all the way up there.
we're not counting that. Plus, we've got about 5 technicians involved. So, there's actually not much change from about $20,000 for this week's expenses on this. So that's why you don't see this sort of thing very often.
That's why we should film it.
You see the turning over now. And whereas for the beam there was very little turning over, then bang, it failed. Now I will confidently predict that this will go all the way over here before it fails. Yes.
How many one of these do they have in Canada? Like these?
They have nothing as big as this anywhere else in Canada, but
Whoa.
there are several in the world that are this big or even bigger. But it is amongst the biggest in the world.
Wow. Oh. Must be a
Well, as you see,
privilege to
Mr.
see this.
Baldwin used to be the Baldwin Wheeler Hamilton Company, and as you see, it was built in August 1961, so it's a lot older than you are. But it's still working just fine. Yes. I'm sorry? Not very heavy at all. This beam weighs, if someone's got the timber sheet,
This is the biggest one
Here.
in Canada.
it's a 10 by 10. If you look at the 10 by 10,
I will. That's why I'm going to copy
the
off
10
on
by
that and
10,
I'm
the
not
dead
copying
load
it
is
right now.
0.365 kilonewtons per meter. It was about 3 meters. It's
Nice
about
to
1
watch, isn't it?
kilonewton, the weight of the beam. Sorry? Put the juice on it, yeah. So John's just, the whole machine is controlled by that little needle valve. He's controlling the flow of oil going into the piston down here, which is driving it. And more modern machines have elaborate servo controls.
Whoa, the shape's
John
really
also
deformed.
operates, but actually I like this one because it's like driving a manual versus an automatic. There's a lot more skill in the manual and a lot more control. So John is just pumping the juice a little faster, which will stiffen it up a bit. Timber is rate sensitive, so if he went very slowly, it would go more flat. But it would be boring. You can maybe spot the bulge here. Can you see that? That it's actually bulging out. That's the Poisson's effect. And the reason it doesn't bulge out on the top and the bottom is simply friction against the head of the machine. So it requires sufficient force to slip it there that it's held.
Oh, sweet.
Now you're starting to hear the
It's like frying eggs. Frying eggs.
pieces break. You see it's break into different pieces. You see
Frying
some
Chinese
shading here.
vegetables.
But look at the amount of displacement we're seeing, right? So this is 5, 10, 15, 20, 25, 30.
Chinese
This has
vegetables.
got shorter by 30 millimeters, right? That's a strain of about 10%. That's about the same strain that the wire took before it broke, right? So this is very ductile material. And it gives lots of warning of failure. It may not be failing in a big stress, but it's failing in a very desirable way.
This is about the prediction.
And
Just above the
just above the prediction. So the prediction failure load was
295.
295. Here we go, 308. So it's
Whoa. Are we gonna just smash it? I smell timber. Zoom in. Oh
It
yeah.
may fly in that direction.
and notice it's still holding the load.
Oh my
Now
god.
it's starting to go down, right? So now we have failure as the pieces come out from the side.
Oh my goodness, it looks like a bomb drop.
3.9 megapascals. 3.9 megapascals.
309.
3.9.
3.9 megapascal. So the stress, the peak stress was 3.9 megapascal. And the tabulated value was 3.6 for the 5th percentile. So it's a very predictable, the difference between the average and the 5th percentile. That's why it's very useful this way.
Ooh. Oh.
That started life as square. You see, it's not square anymore. So the last